Welcome to Rigorous Motion. In this episode, two tests for the convergence of a series, the root test and the ratio test. We prove each one, then meet a series the root test settles, but the ratio test cannot, and we close by proving exactly why the root test has the wider reach. Before the tests, a tool that both of them rest upon. Some sequences never converge, yet they still cluster around certain values, and we need a way to name those values. Here is a bounded sequence that does not settle, plotted as the index advances. The terms bounce between high and low. The even-numbered terms stay high, and the odd-numbered ones stay low. The even terms decrease steadily toward 1. The odd terms rise steadily toward -1. A value that some subsequence approaches is called a subsequential limit. This sequence has exactly two of them. Collect every subsequential limit into one set, which we call E. Here, E consists of -1 and 1. The largest value in this set is the upper limit. The smallest is the lower limit. An ordinary limit exists exactly when these two agree, that is, when the set collapses to a single value. There is a second, equivalent way to see the upper limit, and it is the one the tests will use. Instead of subsequences, watch the tail of the sequence. From index n onward, take the supremum of all the remaining terms, and also their infimum. As n grows, we drop terms from the front, so the supremum can only decrease and the infimum can only rise. The band closes in. In the limit, the band closes down on the interval from the lower limit to the upper limit. So the upper limit is the infimum over n of these tail suprema, and the lower limit is the supremum of the tail infima. Now the fact the tests need, together with its reason. Fix any beta above the upper limit alpha. The tail suprema fall to alpha, so past some index the tail supremum itself drops below beta. But if the supremum of the tail is below beta, then every single term from that index onward is below beta. Apply this with the terms being the nth roots of the absolute values. For any beta above alpha, past some index, those roots all lie below beta. That is exactly the fact the root test rests on. We begin with a single number built from the terms alone. Take the nth root of the absolute value of each term, and let alpha be the limit superior of these roots. The verdict is read straight from alpha. If alpha is less than 1, the series converges. If alpha is greater than 1, it diverges. And if alpha equals 1, the test gives no information at all. Everything turns on how the roots compare with 1. We now prove the first case, when alpha lies below 1. Recall a property of the limit superior. If we pick any number beta larger than alpha, then past some index the nth roots all fall below beta. Choose beta strictly between alpha and 1. Because alpha is below 1, there is always room for such a beta. Mark alpha and slip beta between it and 1. Past some index, every nth root of the absolute value of a term falls below beta. Raising both sides to the nth power, each such term is below beta raised to the nth power. Recall that a geometric series, whose ratio lies between 0 and 1, converges. Recall the comparison test. If non-negative terms stay below those of a convergent series, then their series converges as well. Here, the terms sit beneath the decaying geometric series, and that series converges. By comparison, the series of absolute values converges, and so does the original series. So alpha below 1 forces convergence. When alpha exceeds 1, the roots refuse to settle below 1. Recall that the limit superior is itself the limit of some subsequence of the roots. So a subsequence of the roots tends to alpha, which sits above 1. Past a point, these roots exceed 1, hence the matching terms have absolute value above 1. Recall that in any convergent series, the terms must tend to 0. But here, infinitely many terms have size above 1, so the terms do not tend to 0. The necessary condition fails, and the series diverges. The last case is the delicate one. When alpha equals 1, the test is silent, and we show why with two series that both give alpha equal to 1. Recall that the nth root of n tends to 1, and so does the nth root of any fixed power of the index. Take the harmonic series, the sum of 1 over n. Its nth roots tend to 1, so alpha equals 1. Yet this series diverges. Now the sum of 1 over n squared. Again, the nth roots tend to 1, so alpha equals 1. Yet this series converges. Two series, both with alpha equal to 1, and opposite fates. So when alpha equals 1, the root test simply cannot decide. That settles all three cases and completes the proof of the root test. The ratio test looks instead at consecutive terms. Form the absolute value of each term divided by the one before it. If the limit superior of these ratios is below 1, the series converges. If instead, the ratios stay at least 1 from some point onward, the series diverges. Notice the divergence side asks about the ratios themselves, not their upper limit. We now prove the convergence case. Recall the property of the upper limit once more. Since it is below 1, we may pick beta below 1 so that past some index, every ratio stays below beta. Fix that index. The next term is below beta times the term at n. The one after is below beta times that, and so below beta squared times the same starting term. Continuing p steps, the term p beyond n stays below beta to the p, times that same starting term. Recall once more that the geometric series with ratio beta converges, and that terms below those of a convergent series give a convergent series. Written in terms of n, every term past n is below a fixed constant times beta raised to the nth power. Our terms are below a constant multiple of a convergent geometric series. By comparison, the series converges absolutely. The divergence case is quick. Recall yet again that a convergent series must have terms tending to 0. If from some index the ratio is at least 1, then each term is at least as large in size as the one before. The sizes never shrink, so they cannot tend to 0, and the series diverges. And as with the root test, a limiting ratio of exactly 1 decides nothing. The harmonic series and the sum of 1 over n squared both have limiting ratio 1, yet one diverges while the other converges. That proves both cases and completes the ratio test. Before the subtle case, two series that each test settles at a glance. Take the series whose terms are x to the n over n factorial, where x is any positive number. Recall the ratio test we proved. If the upper limit of the ratios is below 1, the series converges. The factorial cancels almost everything, so the ratio of a term to the one before is x over n plus 1. For any fixed value, this tends to 0. 0 lies below 1, so the ratio test gives convergence for every positive number we might choose. Now the series whose terms are x to the n over n to the n, again, where x is any positive number. Recall the root test. If the upper limit of the roots is below 1, the series converges. The nth root cancels the nth power exactly, leaving x over n. For any fixed value, this tends to 0. Again, the roots fall below 1, in fact, all the way to 0, so the root test gives convergence for every positive number we choose. So each test has a natural home. A factorial invites the ratio test, where the terms telescope. An nth power invites the root test, where the root cancels the power. Keep both in view as we turn to the subtle case. Now a series where the two tests part ways. Consider this series, which interleaves powers of 1/2 with powers of 1/3. Recall the two verdicts we proved. The root test compares the upper limit of the roots with 1, and the ratio test compares the upper limit of the ratios with 1. Look first at the ratios. Along one family of steps, they shrink towards 0. Along the other, they blow up without bound. So the ratios have lower limit 0 and upper limit infinity. The nth roots, by contrast, stay tame. Their lower limit is 1 over root 3, and their upper limit is 1 over root 2. The ratio test is helpless here. Its ratios neither stay below 1 nor stay above 1, so it reaches no verdict. But the root test sees an upper limit of 1 over root 2, which is below 1. The series converges. A second series behaves the same way. Its ratios swing between 1/8 and 2, so the ratio test cannot decide, while its roots tend to 1/2, and the root test again shows convergence. So the root test settled a series the ratio test could not even judge. This is no accident, and we now prove why. Here is the theorem that explains it. For any sequence of positive numbers, the lower limit of the ratios is at most the lower limit of the roots, and the upper limit of the roots is at most the upper limit of the ratios. The roots are trapped between the two ratio limits. That single fact is the reason the root test never loses to the ratio test. We now prove the upper inequality. The lower one is symmetric. Let alpha be the upper limit of the ratios. Recall that for any beta larger than alpha, past some index every ratio is at most beta. If alpha is infinite, there is nothing to prove, so take alpha finite and choose beta just above it. For each step past n, the ratio is at most beta, so each term is at most beta times the previous one. Multiplying p of these together, the term p beyond n is at most beta to the p times the starting term. In terms of n, every term past n is at most a fixed constant times beta raised to the nth power. Recall that the nth root of any fixed positive constant tends to 1. Take nth roots on both sides. The root of the constant tends to 1, leaving beta. So the upper limit of the roots is at most beta. But beta was any number above alpha. Letting beta close down to alpha, the upper limit of the roots is at most alpha itself. So the upper limit of the roots never exceeds the upper limit of the ratios. That proves the upper inequality. Now the other half, the lower inequality. The argument mirrors the one we just gave, with the direction of every bound reversed. Let alpha now be the lower limit of the ratios. Recall that for any beta below alpha, past some index, every ratio is at least beta. If alpha is 0, there is nothing to prove, so take alpha positive and choose beta just below it. For each step past n, the ratio is at least beta, so each term is at least beta times the previous one. Multiplying p of these, the term p beyond n is at least beta to the p times the starting term. In terms of n, every term past n is at least a fixed constant times beta raised to the nth power. Recall once more that the nth root of a fixed positive constant tends to 1. Take nth roots on both sides. The root of the constant tends to 1, leaving beta. So the lower limit of the roots is at least beta. But beta was any number below alpha. Letting beta rise toward alpha, the lower limit of the roots is at least alpha itself. So the lower limit of the roots is never below the lower limit of the ratios. Together with the upper inequality, this completes the chain. Now the promised corollary, drawn straight from that chain of inequalities. If the ratio test proves convergence, its upper ratio limit is below 1. But the root's upper limit is at most that, so it too is below 1, and the root test proves convergence as well. And if the root test is inconclusive, its upper limit is 1, then the ratio's upper limit is at least 1. So the ratio test cannot prove convergence either. Wherever the root test gives up, so does the ratio test. So the root test has the wider scope. Yet, the ratio test is often easier to apply, since ratios of terms are usually simpler than nth roots. That is why both tests keep their place. And a caution on divergence. Both tests can detect it only through terms that fail to tend to 0. Neither one reaches further than that. 2 tests, and a single proof of their kinship. Thanks for watching Rigorous Motion. Next time, we put the root test to work on power series, where the upper limit of the roots gives the radius of convergence. If these proofs are useful to you, consider subscribing so the next one reaches you.